Yeah, thank you very much. So thank you very much, Niels. My name is Florian Schuette, and I'm working at the GeoMar. And I will talk to you about observations of near-inertial wave interactions with coherent anticyclonic eddies. And I did the work together with Daniel Rudloff and Rebecca Hummels, Tim Fischer, Johannes Carstensen, and Markus Dengler most. So first of all, I want to show you a schematic from a rather old paper. So at least it's older than me. It's from Kunze et al. And it shows an anticyclonic eddy. And in this anticyclonic eddy, a downgoing near-inertial wave is indicated. And he proposed that there are possible energy sinks due to this near-inertial wave. It could go into untrapped waves, into turbulence at the eddy base, because it's created in critical layer and then turbulence, or could go into the mean flow. And this is basically goes down due to the effect of F effective. So we heard this a few times now. So it's due to the effect that anticyclones, for this example here in the southern hemisphere, have a positive relative vorticity, and a wave experienced not only the Earth's rotation, but as well the fluid rotation. So you need to add that in an eddy, and so we end up that in an anticyclonic eddy, F effective is always smaller than the local F. And that means for the dispersion relation for internal gravity waves that you expand the area where internal gravity waves could exist, and also add some vertical component to a near-inertial wave. Okay, but so this is somehow known theoretically, but observations of this critical layer trapping are rare, and large uncertainties in the way of magnitude and also how this works exist. And therefore I'm here because I want to show you some there's some guy online, could please mute? We hear some sounds. Okay, thank you very much. No, it's not? Okay, no, it's not. It's muted. Okay, thank you very much. So where was I? Therefore I'm here because I want to show you some observations of this. And so we saw this quite frequently. And I just want to show you this. But before I will show you this, I want to go do some short excursion with you. So I want to show you something where we observationals are a bit struggling with. So to compute the relative vorticity, you all know this. It's normally you got the three parts of it, but we neglect the first two because when we are on a plane, so it's no dv dx minus du dy. So you all should know this. But as when we go with the ship, so we always measure like a line. So we only know something about dx, dv dx, but we don't know the next grid point to the other direction. So that's some problem. And so some guys come up with the poor man's vorticity, so that you take 2 times dv dx, or you rotate it in a long track and a cross track component, and then you take 2 times dv dx to get over this problem. And there are some other guys saying, okay, that it's overestimating the relative vorticity. You should only take it not the double, but once. And there are other approaches where you rotate your system about 45 degrees and somehow compute it back. But what I wanted to say is, so we had one example where the French ship Atalante goes right beneath the meteor for a day or something. So just with the same speed and as I said, a day in not more far away than 500 meters. So we had this opportunity to compute some real relative vorticity and compared it to, because you never know how good these assumptions are. And that's something we did here. So you see in the first place, the one ship method. This is where you rotate your system about 45 degrees. Then the Halle and Pinkel and the Rudnick ones. And the last panel is where we compute the somehow real relative vorticity with the 2 ships. And you could see that there are some differences to this. And in the first part of the time series, they went through an anticyclonic eddy. So this very green thing. And So you see there's somehow an overestimation of about 35% if you use these poor man's vorticity, and it's even more pronounced in the mesoscale eddy. So I just want to show you this before I start, because I found it nice that we have these two ships together. Okay, but now I want to show you the interaction between the near-inertial waves and the eddies, and therefore we thought we look into data where a lot of mesoscale eddies are, and this is here in the Western Atlantic. So we looked into some data set where the Atalante and the Miriam driving around here, and the cross is two times anticyclonic mesoscale structure. And on the right, you see that we took all the crosses that exact same time when they crosses several times some structures, and we compute a ratio between counter and clockwise polarized kinetic energy density of these eddy sections, because near-inertial waves, so we know that near-inertial waves are not only associated to submesoscale motions, but also to clockwise motions. So we tried to find the best section where we could see the most near-inertial wave energy, and this is apparently the red one. And so we look here on the red section, and we cross, as you could see on the left, we crossed an anticyclonic eddy. So the blue one circle is where the sea level anomaly, the satellite data localized the eddy, and the red one is where we localized it with the ADCP data. And on the right, you see the filtered ADCP data, U bar and V bar. And on the, so it's not the same section, it's a bit longer. So on the left, you see the eddy indicated by this dashed line, and you could see already that there is some submesoscale motions at the eddy rim and also beneath the eddy. So here and somehow here. And these black triangles here show where CTD stations were. And at that time, the ship was like at the same position for, I don't know, 2.5 hours doing the station. And so we took these data of the first CTD station and looked into the propagation of the near-inertial wave. And you see here now against depth, time span of the CTD, of the ADCP, of the velocities, again of U and V. And also here is some BKB stretching underneath to get rid of the underlying stratification. And of course, it's a very short time span, but at least you could see that there is somehow an upward slope, which supports the assumption of downward propagating NEVs. And this dashed line is the phase propagation if omega equals F. So it's, and we got some information about the vertical wavelengths, which is somehow around 150 meters. And so we come up with some vertical profiles of F effective. On the left, the inverse background Richardson number, the derived minimum frequency for internal waves, and the vertical group velocity of a theoretical near-inertial wave. And the gray line shows you always the relative vorticity, which is reduced. So when we think about what I showed you the first time, that we have an overestimation of the relative vorticity by 60%. Due to these poor man vorticity, so we reduce it by 60%. That would be the gray value, and the red dashed line is the frequency local F. But I wanted to show you is that the F effective with depth reduces because the most speed of the eddy is at the upper part of the ocean, and you could see that the vertical group velocity is decreasing constantly beneath 400 meters, which means that there's somehow a convergence of energy and some critical layer, and it fits to the data we have because we saw there the most of shear. So that's most likely that there are some actions going on. And we do not only see this in the Atlantic, so I went now into the Pacific Ocean, and you see along a cruise track, the energy in the near-inertial frequency band normalized by Garrett-Monk. So you see multiples of the Garrett-Monk spectrum, and you see that there's a lot of power going on this small part there. And it's not surprising that there was again an eddy. That's the ADCP data again against depth, and you could see the anticyclonic rotation. And even in the unfiltered data, you see here this layering of data, and this is U bar V bar, and you again see the clockwise polarization of the velocity. So it's again near inertial wave activity. And we also did some microstructure measurements in an eddy. It's also another eddy, but similar area, also Pacific and anticyclonic eddy. So the other part of the eddy is not shown. It's here. So only the red, the one flank is shown, but it's a microstructure profile in the core, in the eddy core, and you could see that enhanced dissipation rate of turbulence kinetic energy is associated to these layers here, of course, and we have a lot of shear here, so yeah, a lot of mixing could be measured. So on average, we have a 10 times higher mixing in the eddy at the eddy base compared to the background where no eddy was. And we also saw it on moorings, for example. You see here a mooring and an eddy propagated over this mooring, and we have an ADCP looking upward. We're seeing from the surface the first 250 meters, and at 400 meters we got a point measurement at 700 meters. And if we filter this again, we see that, for example, at 400 meters, you see there's a lot of action going on in the eddy core and beneath the eddy. So at 700 meters, there's nothing. So it's again an example of the trapping of near inertial waves in an anticyclonic eddy. And the question, of course, now these are all single observations. The question is now, how big is the effect on a global scale? So we want to somehow assess this effect for I don't know, 500 eddies. And therefore we looked into all the data we have at the GeoMar. So that's all the ADCP data you could see, mostly Atlantic, a few Pacific cruises. And we try to find every time when we cross an eddy with satellite data. This is one cruise as an example. And then we want to come up somehow with an composite of near inertial wave energy within anticyclonic eddies. And this is just a rough plot. So that's an ongoing project, and we hope to do this now. And this is just a rough plot of all the data we have. So these are, so there are a lot of eddies, and around 40,000 kilometers we did in anticyclonic eddies and in cyclones, and we normalized them and located then in their difference between from the eddy border to the eddy core, and hope now to get a mean picture of this. And why is this important? So of course it's important, as you all know, due to your project, for the energy distribution, but also for the tracers. For example, in the Pacific, you see the oxygen minimum zone here on the left, and that's exactly the depth of an eddy, of the eddy base, where we then enhance some mixing and make a ventilation from the oxygen minimum zone from underneath. And I haven't seen something about this effect, or also for nutrients, for example. So that's also some strong gradients in nutrients there. You mix up nutrients to the surface, so it's not only for energy but also for the tracers. Okay, to sum this up. So we got an estimation of relative vorticity in the observations, and saw that this, how we do it all the time, the Poorman's vorticity is somehow overestimating the relative vorticity, and its explicitly in an eddy, it's even stronger overestimating. And then we analyze an anticyclonic eddy in the Western tropical Atlantic, and show that the velocity is intensified in the upper part, and the relative vorticity is decreasing with depth. So hence the derived vertical group velocity of the near inertial wave also decreases with depth. And this leads then to a critical layer and probably mixing at the eddy base and at the eddy periphery. And there are a lot of other examples. I showed you 2 or 3 for the Pacific, where we saw similar structures. And also we had there some measurements of the microstructure and saw that it's, yeah, the mixing is 10 times higher there compared to the background. And to assess the importance from this effect to more global scale, or larger area, we want to get a composite now from all the data we have. So yeah, thank you very much.